Hello everyone. Uh, as you people know, we have completed the pyrazole heterocyclic compound called pyrazole. That is, we have completed the aromaticity synthesis as well as the chemical reactions of the pyrazole. So let's and medicinal uses also have discussed, and you can see the videos as well as the PPTs. And today we are going to discuss the other heterocyclic compound, imidazole. So what is this imidazole? Already we have discussed each and every nomenclature of the heterocyclic compound in detail. So you should able to recognize soon after I have written the imidazole. Ol indicates it is a 5-membered compound, and imidazole, it is a common name. It is not the it is not the IUPAC name in the heterocyclic nomenclature. It is the trivial name we are using. Okay, so this is the structure of the imidazole. This is the structure of the imidazole. So what it is? 1, 3 diazole. This is the IUPAC nomenclature of the heterocyclic compound imidazole. This is the IUPAC system of the nomenclature. That is, the nitrogens are heteroatoms. The heteroatoms means nitrogens are present at first and third positions. So we are calling 1, 3 diaza. Diaza means 2 nitrogens at 1 and 3, and ol for 5-membered ring. This is the IUPAC system, but it is well known by its trivial name. Few of the compounds are well known only with their trivial names. For example, this is the imidazole. Imidazole is well known. 1, 3 diazole is well known as imidazole, that it is well known by its trivial name only. So whenever if you see the nitrogens at first and third positions and a 5-membered ring, you have to call it as an imidazole. Okay, so let's discuss the things related with the imidazole. And before that, what is the difference between the previous heterocyclic compound and this, that is pyrazole and the imidazole? The small difference is the position of the second nitrogen, that is the other nitrogen. In both of the cases, pyrazole and imidazole, the first nitrogen is present at its same position, that is at first position. But in the pyrazole, the other nitrogen is present at second position, whereas in the imidazole, the nitrogen is present at the third position. So only small difference, that is the position of the second nitrogen. Pyrazole, it is present at second position, and imidazole, it is present at the third position. Due to the small difference, most of the properties, the imidazole and the pyrazole will share the common properties. So whatever the things we have discussed with the pyrazole, it will be same, mostly 90% same with the imidazole, because the ring structure is very similar. Both of them are very similar, except the position, small change, that is nitrogen is present at position 2 in pyrazole, whereas it is present at the position 3 in the imidazole. So let's go to the aromaticity. Same, the aromaticity is also same, exactly same to that of the pyrazole. Okay, if you are clear, if the aromaticity of the pyrazole is clear to you, then it is also very easy. So here also, so when I'm keeping the lone pairs, you have to understand clearly by this lone pair positions only. Okay, this first nitrogen and third nitrogen, right? The first nitrogen have pyrrole behavior, and third nitrogen has pyridine behavior. Already I have told you. In the case of the pyrazole, same, the first nitrogen have pyrrole behavior, third nitrogen has pyridine behavior. What is this pyrrole and the pyridine behavior? Once again I am repeating, the lone pair, that is on the first nitrogen, it is present inside the ring, that it is involved in the pi bond formation, that it is left unhybridized and it is involved in the pi bond formation. On the third nitrogen, lone pair is outside the ring, which indicates it is involved in sp sp2 hybridization. Here this is involved, this lone pair is involved in pi bond formation. Okay, that is clear now. And coming to the hybridization, how many carbons are there? Same here, 3 carbons, 2 nitrogens are there. So each of them, all of them are sp2 hybridized. All of them are sp2 hybridized. And from each carbon, so what is left over? Again, I am not discussing the electronic configuration and everything. You can see it from the pyrazole. Exactly what is the aromaticity of the pyrazole is exactly the Xerox copy of this imidazole. So once again, I'm not discussing any electronic configuration. Once check with the pyrazole. So I'm giving the other points. So there are 3 carbons and 2 nitrogens in the imidazole, right? So each of the carbon undergoes sp2 hybridization to form the following sigma bonds: Cc, Cn, and NH, and yes, these are the sp2, that is sp2 hybrid orbital of one carbon forms the bond with the sp2 hybrid orbital of the other carbon to form the Cc bonds. Okay, this is our Cc bond, and this is the Cn bond, sp2 hybrid orbital of carbon with sp2 hybrid orbital of the nitrogen. This is sp2 hybrid orbital of the nitrogen with s orbital of the hydrogen. So from this sp2 hybrid orbitals, sigma bonds are formed. So sigma bonds, I am highlighting with the blue pen, these are the sigma bonds. So okay, outside the ring is done. So what about these pi bonds, how these are formed? You know, so in each of the carbon atom, there is an unhybridized pz orbital. Pz orbital is left unhybridized with 1 electron each. So totally 3 carbons. So there are 3 electrons which are left unhybridized. Unhybridized p electrons forms pi bonds. The thing that are involved in the sp2 hybridization will not form any pi bonds. They will form only the sigma bonds, that is the bonds which I have highlighted. Next, the unhybridized p orbitals from each carbon lo, you can check the electronic configuration from the pyrazole. 1 pz electron is left unhybridized. So totally 3 carbons. So 3 electrons from 3 carbons are left unhybridized. Next, coming to the nitrogen. First nitrogen lo, so what happens in the case of first nitrogen? Lone pair is left unhybridized. So it will forms it is involved in the pi bond formation. So lone pair means how many electrons? So 2 electrons. Lone pair means 2 electrons. First nitrogen, lone pair, that is 2 electrons, or you can say lone pair is left unhybridized. By seeing the diagram only you have to understand. If it is present inside the ring, yes, it is unhybridized. That means it unhybridized means it is involved in the pi bond formation. That's it. Next, third nitrogen. In the case of the third nitrogen, you can see the lone pair I've written outside the ring. That means this lone pair is involved in the sp2 hybridization. So you should not count in the case of the pi bond. So in like the carbon, same pz orbital with 1 electron is left unhybridized in the case of the third nitrogen also. So totally how many electrons are left unhybridized? From carbons, 3 electrons. From first nitrogen, 2 electrons. From third nitrogen, 1 electron. 3 plus 2 plus 1, that is equals to 6 pi electrons. 6 pi electrons are left from all the atoms in the pyrazole. From each carbon, 3 carbons are there, 1, 2, 3, 1 pz electron. From nitrogen, you can see clearly pi bond formation lo involve in the 1 lone pair, that is 2 electrons. 1 from each carbon, 1, 2, 3 from carbons, 3 electrons. From nitrogen, this lone pair, that is 4, 5. From this nitrogen, you should not count this lone pair, it is present outside the ring, so it is involved in sp2. So sp2 means this bond. So for this bond you have to count only the unhybridized. So which is left unhybridized? Same like carbon, 1 pz electron with 1 electron is left. From this nitrogen 2 electrons, from this nitrogen 1 electron, from each carbon 1 electron. So totally 6 pi electrons. So Huckel's rule, 4n plus 2 pi electrons is that Huckel's rule, that 4 into n, that is n is equal to number of rings. Pyrozole is only one ring, right? 4 into 1 plus 2, that is 6 pi electrons. So 6 pi electrons means 6 electrons means it should form 3 bonds, right? But how many bonds are there here? 1 and 2, and the other is represented as a lone pair. That is 1, 2, 3, 4. One bond is equal to 2 electrons. One bond 2 electrons, the other bond 2 electrons, 2 plus 2 4 electrons, and a lone pair 6 electrons, 6 pi electrons. So hence 3 bonds or 2 bonds and a lone pair. Okay, so hence imidazole is also aromatic. Why? Because it is satisfying the Huckel's rule, that is 6 pi electrons. And you can draw the this diagram, that is showing the unhybridized p orbitals. Carbon, this is carbon, carbon, p orbital which is left unhybridized. This is only representation of unhybridized p orbitals. Okay, so from each carbon 1 electron is left over in the pz orbital. For this electronic configuration, please refer the pyrozole. I have clearly explained. Okay, and in the nitrogen, first nitrogen, what is left? First nitrogen, the lone pair is left unhybridized. In the second nitrogen, only 1 electron is left unhybridized. Okay, and the lone pair is involved in sp2 hybridization, so it is not involved in the pi bond formation. Okay, so 1, 2, 3, 4, 5 and 6. You should not count this. Why? Because in the third nitrogen the lone pair is involved in sp2, so only 1 electron is left unhybridized. Okay, so totally 6 pi electrons forms the aromatic sextet. That is, aromatic sextet means it should contain 6 pi electrons which are unhybridized. 1, 2, 3, 4, 5 and 6. This is involved in sp2 hybridization. That's why kept outside the ring on the third nitrogen. Okay, so and one more thing, the plane of the pi bonds is always perpendicular to the plane of the sigma bonds. In this you can clearly see the dumbbell shaped thing, that is, it is related to pi bond, and this is the sigma bond. See, this is pi bond and this is sigma bond, so it is L shape, that is right angles. So the plane of the sigma bond, this is sigma bond, is always perpendicular to the plane of the pi bond. This is pi electron. Okay, so unhybridized p electron always represents the pi electron. Okay, so always the sigma bond is perpendicular to the plane of the pi bond. Okay, this is the aromaticity of the imidazole. Okay, hope it is very clear, and let's go to the other reactions. Other part, that is synthesis of imidazole. Synthesis of imidazole. For every topic or for every side heading, you have to draw the structure once again. NH, try to keep the lone pairs also. First nitrogen lo inside, third nitrogen lo outside the ring. Okay, it clearly indicates one lone pair is involved in pi bond formation, one lone pair is involved in sp2 hybridization, that is sigma bond. Okay, now coming to the synthetic methods. First method, very important, Radzievskis synthesis. The name is very complicated. He's the discoverer, maybe. Radzievskis, whatever you pronounce, it's okay. Radzievskis synthesis. What is this Radzievskis synthesis, and what are the starting materials we are going to use here? Okay, very easy. We are going to use 3 compounds, 3 starting materials. One is a dicarbonyl compound. dicarbonyl compound. You know, that is the compound which contain two keto groups is called as a dicarbonyl compound. One other thing is ammonia, and the other thing is aldehyde. Okay, these three are going to use in the case of the Radisz-Chewski synthesis. One is dicarbonyl compound, the other is ammonia, and the other is the aldehyde. Okay, so let us start dicarbonyl compound. So this is the dicarbonyl compound. This is one carbon, this is the other carbon, this is one alkyl group, this is the other alkyl group, these are the two keto groups. A dicarbonyl compound. Next, reacts with 2 moles of ammonia. Okay, so what happens when it is reacting with the 2 moles of the ammonia? So both the oxygens gets converted to, that is eliminated, and the amine groups occupies the position of this.